3, 2.
Okay, today is November the 24th, 2017. What I want to show you today is I made a video the other day on how to measure the inductance of audio output transformers, and it worked pretty good sometimes, but it wasn't very reliable. Here's a much better way. Right here, I got this article from this website right here. If you want to go out and take a look at it, and it talks about measuring with a sine wave. Well, one of the things that we wanted to do was be able to use an oscilloscope and be able to measure the phase difference. They show you a little window right there, and this one is built in such a way that you can use an oscilloscope across it. What we're doing is we're going to measure the voltage across the inductor, and we're going to measure the voltage across the resistor. The internal resistance right here of this particular generator is 50 ohms. Well, since our generator is a 600 ohm, what I've done is I've put a 10 ohm resistor across it right here. It's not shown in here, but it is in my LT Spice model. You put a resistor across here to swamp this so that this does not become a significant part of the equation. So we put our scope here, and what we do is we measure the phase difference. Now, in the other one, what we did is we just measured we measured half the voltage. We measured it so that, and adjusted this R so that half the voltage was across R as was across L. This one, it doesn't really matter. R does not have to be any particular value. As the values of L, right here, as L go down, like down to say maybe 500 millihenries, this needs to go down to say 300 ohms. As this goes up to say 50 henries, this value up here needs to be about 10K, maybe even 15K. The higher you make this resistance, though, the more noisy your oscilloscope channels tend to become. Now, the difference between the other one, which was a scalar measurement, which only had one dimension, and this one takes into account all the vectors. It's a beautiful article, really. See how this vector is green, this one's blue. Those are the main ones. And here's the vector right here, the blue vector Vx. Here's the blue vector Vx. VG right here. Here's VG. They did a really nice job, and all of their math is exactly right. Now, in these types of measurements where we're using cosine and sine and angles, all of the voltages are peak, all of the currents are peak, and the angles are in radians. So we always have to convert our degree angle measurements to radians. You just divide it by, if you have an angle and it's in degrees and you want to convert it to radians, you divide the angle in degrees by 180 over pi. And I'll show you how we derive pi. Here's the rest of the equations, and ultimately what we get is this right here. And we measure the phase difference between these two. Now, in this particular case, this oscilloscope has the nice feature of actually just printing it out. Well, my oscilloscope doesn't do that, so we actually have to put in our cursor right here and physically measure it, and I measure it in milliseconds and then convert it back to radians. And then ultimately down here we get L, which is x of L over, we call this omega, 2 pi f. Anytime you multiply the frequency in hertz times 2 pi, you get the frequency in radians. I think everybody knows that. So while this seems like a no-brainer, actually determining x of L and taking into account all of these vectors is how you get the right answer. And I get the right answer every time, everything from about 500 millihenries up to 50 henries, which is sufficient for making measurements of transformers. Okay, let's make some measurements. Now down here I've got two really beautiful pots. Let's look underneath this thing so you'll see what's under there. This one is out of a GR instrument, some GR impedance bridge, and then this is a multi-turn 20K, just some military surplus stuff, just some really beautiful potentiometers. So I can dial it right in. You can use those, or since the value of R is not very critical, I found out that by using these precision resistors, and again, they don't have to be precision, but you do have to be able to measure them and know very accurately. See, this one is 383 ohms. It could be 300 ohms, it could be 400 ohms, it doesn't really matter. But if we're going to measure low inductance values, we need a low inductance resistor here. Let me put this in there so we get the right amount of phase shift. So let's measure a standard inductor. Right here's one. That one is 1 Henry. See how close we can get to 1 Henry of it. Okay. Also, I've noticed that you need to set it up on something and not get any kind of interfering noise source next to it, like a fluorescent lamp. I'll show you that in just a minute too. So if you want to make one of these setups so that you can measure inductance, you've actually got to make yourself some sort of a legitimate test jig, because if you just run wires and clip leads like I did in the beginning with alligator clips on both ends, you end up with a very unpredictable setup, and you won't get the same answers twice. Okay, we know that this is 383 ohms. Let's go over to the Excel spreadsheet. I want to make this as quick as I can. This right here is the frequency. Here's our frequency, and here's a number that we're putting in. That's something I dialed in, so let's just put in 383. Now where we're getting this number right here, this is 70 hertz, but I'm putting it in exactly as the meter reads off, 70.17. Here it is up here, 70.17, and I'm setting the voltage that I excite the circuit with it at 100 millivolts, 0.1 volts. Well, it's loading it ever so slightly, so it's 0.0997, and we'll put the numbers in exactly as we get them. There it is, 0.997. These numbers are staying set from evens from last night. Now we measure the RMS voltage right here, but we're going to convert it to peak out here. Okay, we measure the RMS voltage. We're going to put that in right here, and here it is right up here. Everything's hooked up, and the way that I get the best reading is I stop it, and this meter will do a min max. So this is in millivolts, so this is 0.067673. Okay, so we type that in right here, 0.067673. Hit enter. Now here's the fun part. We've got to measure the phase shift between the voltage across the resistor and the voltage across the inductor. And we do that right down here with the oscilloscope. Okay, if we move these traces together, you can see probably a little bit better how they are out of phase. Can you see that phase difference right there between the two? They don't have to be equal in amplitude. That really doesn't matter. But what we have to do is measure the phase difference. So what I'm doing is I'm moving my cursor right here. See how I can move this around? I'm putting this one, or either one, it doesn't matter. You can put this one on the right or on the left, but I'm putting it right smack in the middle of the top, right at the very crest of this sine wave. And then I go to the other one, and I put it, this right here, that's what I'm moving around. I put it right at the very crest of this sine wave. Now you could do it at zero cross, but if you do it at zero cross, then you're going to have these two of the same amplitude. So I don't want to go to that much trouble. So we're measuring the phase difference from crest to crest right here. And here it is right there. There's the delta, 1.35 milliseconds. Now we go back to our spreadsheet and we type in 1.35 and hit enter. And right here's our L value. Remember, this is our standard calibration inductor, and it's 1 Henry. It measures 0.98 Henries. And it does it every time. It's really very, very good and reliable. Got to be really careful. Got to make sure that you get all your numbers in straight. Now, I talked about RMS. See, I've got right here, enter RMS, generator voltage, enter RMS across the inductor. Well, I put in RMS because that's convenient, and then right here I just convert it. I take the RMS voltage and multiply it times the square root of 2. I do the same thing right here. I don't know if you're familiar with Excel programming, but it's really a powerful tool. And now here I derive pi, because we're going to have pi. Pi we know is 3.14159 and thereabouts, but putting in a constant like that really does not give you the best answers. It's actually better to derive it. And for those of you that are really interested, here's how you derive pi. It's actually 4 times the arctan of 1. Now this 1 is a radian, not degrees. 4 times the arctan of 1. If you put it in like that, the Excel will assume this to be radians. And that will actually give you pi. That's the definition of pi. That's one of the definitions of pi. And then you go down here, and then the formulas get pretty screwy. The square root of all of this stuff, the cosine of angles and sines of angles squared and what have you. It's just right out of that article exactly. Here it is again. See, like here's how I convert things to radians by multiplying it times 180 over pi. See, pi is in cell E5. Here's E5. That's the way that's done. And then ultimately you come down here, and there's L, and it's really very, very good. Now that's for 1 Henry. Let's go up to something like let's use a calibration inductor of 17.5 Henries. Okay, here's that one. And here's 17.5 Henries right there. Let's see how close we can read that. Okay, so we just take this guy off. We put our other inductor on. Again, raising everything up, trying to keep everything away from metal and anything interfering. Now we're going to need a different resistor here. We can dial it in with these pots, but that would just kind of lengthen it. Here's another precision 1/4% 10K pot, 10K fixed resistor. Let's just put it in. See, what I did is I installed these connectors right here, so that when this connector's in, it shorts this guy. It doesn't matter where this is at. When this one's in, it shorts this guy. So I can short either one, or I can short this one. I can use either one or both or whatever. Gives me all the options. But we're going to use a fixed resistor 10K. So let's go back over to our spreadsheet. We'll do this one in one more. And then instead of 383 ohms, we're going to type in 10,000. So there's our 10,000 ohm resistor. Our voltage up here varied ever so slightly. Now it's a 100.1008 volts. So just to be as accurate as we possibly can, 0.1008. Okay, now we've got to measure the voltage across it. And the way I use this meter is I put it back in and let it run for a second. It doesn't have to run very long, of course. And then I can change the rate here to medium or fast or slow. It doesn't really matter. And then I just freeze it in max. And then it settles down and we can read it, because we can't read it with those little numbers rolling like crazy. Okay, that's 56.025 millivolts. That's 0.056025. Enter. We're getting close. Now we got to measure our phase angle again. As you notice, it changed, but the amplitude is about the same. The amplitude is about the same because I changed the resistor to 10K, but I also changed the inductor from 1 Henry to 17.5 Henries. And of course we can multiply this up if this makes things easier. But you see, it's starting to get noisy just a little bit, and it's not all that much. So all of the measurements are somewhere between about 900 microseconds, which is 0.9 milliseconds, up to maybe 2.5 milliseconds. That's what I have found to be the range from measuring down at a 0.5 Henry up to 50 Henries. But anyway, let's set these guys back in the middle as best we can. That looks like the peak to me. And we move this one over to the peak of the bottom one, so we're measuring from the peak of this one to the peak of that. We're measuring time. It looks like it's 1.65 milliseconds. Let me see that. That's about the best I can do. 1.65. Okay, now let's put 1.65 back in here. 1.65 milliseconds. And again, I convert all of that to frequency and then back to radians. And it says right here that our L is 17.511 Henries. And our inductor is stamped at 17.5 Henries. That's pretty darn close if you ask me. I'm really impressed with this method. It does take some a little bit of sophisticated equipment, but by golly, it also works, and it works every time. Okay, let's do like one more. Here's the one that started this insanity, and that was this James transformer. Audio output transformers. How do we directly measure the inductance of audio output transformers? Well, that became quite a project, but this is how it's turned out, and it's actually turned out really well. I'm measuring plate to plate. This one's got screen taps. We're not going to measure all that. I don't want to go through all the measurements. We could be here for an hour or two, but we'll just measure plate to plate. We can measure that. We can measure those high values. We can certainly measure the low ones. Okay, now we got to go through this process again very quick. Our voltage up here didn't change. Our frequency didn't change. The 70.17 is not important. I'm just trying to set it on 70. But I've got a variable, you know, I can vary it, so that's as close as I can get. But I'm putting the numbers in exactly as I read them. Our resistor's still 10,000 ohms. There's our voltage. Now we got to measure this voltage again. Go back to rate. Let this thing run for just a second, right up here. And then we'll stop it at its max. That's 67.46 millivolts. Let's type that in. See, a while ago for the other one it was 56 millivolts. Now it's 67. It's 0.06746 volts. And our time down here, 1.65 milliseconds, looks like it's really pretty darn close to the same. I might move this one ever so slightly. Get my head in the way here. I gotta measure one at the very peak there and the very peak there. That's close I get. That's 1.85 milliseconds. Okay, let's go with that. Now let's type it in. So we went from 1.65 to 1.85. Hit enter. And there's our inductance of that transformer from plate to plate. It says it's 20.8 henries. And 20 henries, I'm very confident, is the right answer. Now that one doesn't have it stamped on there, and I don't think you're going to find many, if any, documents that actually tell you what the inductance of your output transformers are, because mostly people don't need it. But what initiated this project was we were wanting to model these transformers in LT Spice. And then if you do that, you do have to know these numbers. Of course, you got to know the number between the plate and the screen grid and the center tap too, but that's just another set of measurements. And it all works out. Let's do one more transformer, okay? Because it's actually pretty quick now, just depending on how you got it set up. Here's a really interesting one. This is a Chicago Standard. A really nice transformer. I think I'm going to build something out of it. I'm going to measure between plate and plate of this. By the way, I do not measure the inductance of the secondary winding. It's just not necessary. I do the math and calculate it. I think you've seen that done in some of the other videos. Okay, now we're measuring plate to plate of this one. You'll be surprised. Okay, look how this changed right there. You know what that indicates? That indicates much more inductance. See how the amplitude of that one went up? And also the phase shifted quite a bit too. Pretty much everything else is going to be about the same. It's still 0.1008, 70.17, all these numbers. This one will vary somewhat. Our voltage will vary. And our time is going to vary. And there's our voltage. Let's set this guy up down here. It's going to be very narrow. As the inductor gets larger, the phase shift gets less. Okay, this one is splitting the top one. And now we got to split the bottom one. And this is probably about as high an inductor as you're going to want to measure. That's 1.1 milliseconds. I guess that's about as perfect as we can get. 1.1. I'm doing this in a slightly different order. 1.1 milliseconds. And then our voltage here is 85.85 millivolts. So we'll type in 0.08585. Can't believe I haven't made some typo error here. Look at there. 41 henries. I get that consistently. You know, I don't get exactly 41.23000, obviously, but the answers are right. And the answers vary from each other only 2 or 3%, if that much. Now, let me show you something else. Look how nice and clean the signal is. But if you bring a light source over to it, look, I just turned it on, and can you see already how all I did was turn the light on, and look at the distance of the light to the transformer. Now watch what happens when I bring this thing down close. Can you believe that? That's how sensitive these big inductors are. These high value inductors. It doesn't matter, I promise you, it doesn't matter if it's this guy or this guy or this type of transformer. This is like for a pair of push-pull 6BQ5s. Or if it's this one right here. This is a big 50 watt 10K primary. It doesn't matter which ones I have hooked up, including this one. The noise does the same thing. So in the beginning I was making all these measurements on this other workbench. It had a steel top. This is a wooden top. Of course there's steel underneath it. So you got to have yourself a nice setup. You got to have yourself some calibration resistors or some pots or however you want to do it. These 4 resistors right here from 300 ohms to 10K, these are 1K and 2K for something in the middle. You want your phase shift to be enough that you can read it reliably. And yet you want it low enough so that you don't start picking up too much noise. Like if you put a 50K in here or 100K, it starts getting really noisy. By the way, I'm using 1X probes, not 10X. I don't have to use the 10X. The 10X just makes the noise go up. So I have found out that this is actually quite a reliable way to measure the inductance of these big guys and get the same number every time, and get a number that agrees with my little standard inductors. There's the 17 Henry, there's the 1 Henry, there's another one over here that's 500 millihenry. It does the same thing. It'll measure just as accurate. And then I get what I expect. I expect these to be about 20 henries. This one surprised me at 40. This one measures about 20 henries too. If you just don't have the time or the setup to measure them, you can model these transformers pretty much as 20 henries from plate to plate. And I think you'll come out with a pretty good answer there at LT Spice. Now, I'll show you one other thing here. Again, if you don't want to use these resistors, let's just take this one off. Now let's use our shorting bar to go over here to this one. Now I've shorted my R, so now this one is the one that's open, and I can dial in. What I have to do to dial in, though, is I have to put my my resistor here across the output. This is a really nice, accurate little meter, but then I can dial this in. Watch, I'll dial in 10K, 8, 9. Whoops, went a little bit past it. So you can use potentiometers for it if you want to. And you can dial these multi-turn pots into exactly what you want. We're only off. Don't be nuts about it. 10,008 ohms, 10,005 ohms. Give it time to settle down, and then you can plug those numbers in too. You can use that as a 10,000 ohm resistor, and you'll get exactly the same answer as you do by using this fixed resistor. So it's kind of interesting how the project started out to model transformers in LT Spice and changed into how to directly measure the inductance of audio output transformers. But I have found it very interesting. My many thanks to Bob up in Iowa for I don't know, we've probably exchanged 100 emails, and he's got an approach measuring the R losses and the iron losses. That's an approach he's taking, and I'm anxious to see how that turns out. But I hope this helps you guys. Those of you that like to make these measurements, I love to make measurements, and it's my pleasure to make these videos, so I hope they help, and I appreciate you watching my videos.